Okay, okay. So let's see. We're going to shift slightly into just a little more applicable ways of using some of the elasticities. There's some neat little formulas that we'll kind of bypass the guts on that are helpful. So the first one is a marginal revenue formula that's related to price and elasticities. So let me just give you the formula here. Marginal revenue is equal to price times 1 minus 1 over the absolute value of the elasticity of demand. Now that's a lot to swallow. And if a couple of you are math geeks out there, I'll let you derive that. You can derive this expression from what we've done before, but otherwise, take my word on it. We see that there's a connection, right? Because we got marginal revenue in here. We've got elasticities playing a role. Depending on where we're at, the elasticity changes. So it turns out it all simplifies down to this little expression here, that the marginal revenue of the whatever unit, we didn't put any units on here. So if this is 75 units, just to make up a number, so at 75, the revenue generated by the 75th unit, taking all things into consideration, is that amount, whatever that number is right there, is the marginal revenue. That number is a function of that price times 1 minus that elasticity, whatever that little guy is right there. That's all the pieces of our puzzle. There's a connection there, a mathematical formula that puts us all together. Okay? So in the first or second chapter, we talked about extent decisions. Should we do it? Should we not? Right? We learned, hopefully, that if the benefits of an extra unit, a new decision, whatever you're changing, if the benefits of that change are greater than the cost associated with that change, the proper cost that should be associated with that change, then as long as the benefits exceed the cost, do it. If they don't, right? That was the whole marginal analysis. But we can kind of bring that back here now for the company. If we can use this formula, given our current pricing, if we know the price and the elasticity of demand, we maybe had an economist or somebody do some sort of study here that we've got the elasticity, we know what we're currently charging for our price, we can now reasonably estimate the revenue of an additional unit. So if I was to go from 75 units to 76 units, well, it's approximately that number, right? It's going to be a little less, but it's about that number at that point. So now we can bring in the cost into the picture. And so let's just start off here with recall marginal analysis. If marginal benefit is greater than marginal cost, do it. If not, don't. Well, now tying this back to this chapter and these numbers that we're doing, we can start to think about how our revenue and cost are doing. So, for example, our optimal quantity is where, in a business case now, if the benefits are captured by dollars, we're going to substitute in marginal revenue here for this. So our optimal quantity that we're going to produce is where the revenue generated by the last unit, and now I'm going to go ahead and substitute in this new formula, 1 minus 1 over E, the elasticity. The optimal quantity occurs where marginal revenue equals marginal cost. if we do a little bit of math and rearrange the terms, we can put this expression of marginal revenue. Let me pause there for a second. Is everybody with me on this? So the optimal quantity would be that. I see a pause. One way to think about it is if the most general case would be, there's our marginal benefit curve, which is downward sloping. As I consume more Oreos, the benefit that I get from the 10th Oreo cookie is much less than the benefit I get from the first Oreo cookie, right? So the benefit curve is actually the demand curve typically. We think about the demand curve and the marginal benefit curve being one and the same. Marginal costs are upward sloping due to the law of diminishing marginal product, which see that restaurant example if you haven't seen that. So the optimal quantity is right here. Why? Because if I'm here at Q1, the benefit is greater than the cost, but you're leaving a little bit on the table, right? Because if you went to here, the benefit of this extra marginal unit is here and the cost is there. So do it. What about this one? Do it. Do it, do it, do it, do it until they're equal. Whoops, if I went to Q5 over here, the cost associated with that unit was much greater than the benefit. That was pretty stupid, bonehead deal to do. So back off, cut back production. So you want to start moving this direction with your quantity. Cut back, oh yeah, the cost, I see the profit is, or the losses are getting smaller now, right? So I'm moving the right direction. So I want to move this direction to this optimal quantity. Question on that? That's real important to go through other things here. Okay, so we're going a little bit on faith with the mathematicians that this sucker is equal to this sucker, right? And now we're saying that the optimal quantity is that this is equal to this. So what I want to do next then is rearrange the terms a little bit. So we can rearrange the terms. If we I'm not going to do all the math steps here, but we multiply through the P, we get the marginal cost over here, we swing this over there, and just so I don't screw it up when we rearrange it, we get price minus marginal cost over price equals 1 over the absolute value of the elasticity. Now this is a neat little modification. You guys have heard of markups, right? That companies mark up, mark down. Yeah, because you were in the retail sales with the phone, right? So they come in and we're going to mark them up, and the boss might just say, well, mark them up 30%, mark them up 100%, whatever. Well, this is kind of a markup. It's similar to a markup concept, right? So we've got price minus marginal cost divided by the price. Right? It's kind of similar to a markup. It's not quite the markup, because a lot of times you might think, I bought these for $100, I'm going to mark them up 30%, so they're going to be $130. That's not quite what's going on here with the math. So bear with me, but it's kind of conceptually like a markup. So price, so in fact, it'll be referred to as a markup, but some people's markups are different than other people's markups. But you've got kind of this difference between what you're selling it for and what it cost you. Which is what we were dealing with on the demand curve, the price we were getting at versus whatever it maybe had cost us, divided by that price, is 1 over the elasticity. And this kind of gives you the optimal markup. Because now if you know the elasticity of demand is 1.2, assuming we're on the elastic range, because if we were on the bonehead range of the demand curve, we should have been increasing price anyway, right, for the reasons we just did. So that's another little lesson here, is that if you're over here, you just need to raise price. So once we're over here, though, if the elasticity of demand is some number, calculator for me, 1 divided by 1.2, 0.83. And so that should be matching of gives you a nice way to plug the numbers here on the markup. All right, so why is that kind of thing? Oh, wait, I didn't get this. Shoot. Let's just take a quick little pause, because I do kind of want to erase this. This is the only thing. This is all correct. Kind of. Well, no, it's totally correct. This turning into this is totally correct. What's not quite correct, though, is that the percentage change in quantity is not this upstairs thing, actually. It's real close, but it's not quite there. And that was kind of bothering me, because if you were to calculate this number like we did, that looks like 2.5%, doesn't it? But it's not. That's not what this number is. We did a simplification here that I didn't show you, that I normally show you, but I didn't want to drag down class and show you this little step. But now I'm coming back, and I'm never going to do it again. Okay, so I was trying to save time, being the economist in me. But this average here was actually 97.50. Remember, we were taking the midpoint between 95 and 100? So that was 97.50. What we were really doing was dividing by 2 to get 97.50, and same thing down here, actually. We were taking 1150, 21 divided by 2. If you flip those 2's over, they cancel. But to get the real percentage change, you got to multiply this times 2. So now if you take this times 2, it's actually a 5% change. This is totally legit. This now is okay? So it's actually a 5% change in price and a 2% change in price. That ratio is the right ratio. Now, I'm not just doing that for playing math games. I'm actually doing that for a reason. Sometimes you'll be faced with a problem, and you'll see it in your text, where you might be given a percentage change in the elasticity, and you have to calculate the other one. In other words, we use just this part often. So let me give you an example of how that would work. So suppose the elasticity of demand is 1.2, and in absolute value, so the elasticity of demand is 1.2, and you decrease price 10%. How much do you expect to sell? Now we start to see the power of the elasticity in predicting how much more we're going to sell. So we fall back to this formula. We don't even get into the guts of this one. We fall back to this one. I don't want you to forget this one right here. And that is the elasticity of demand equals the percentage change in quantity demanded over the percentage change in price. Or we've got now a 1.2 negative, because I stripped off the absolute value, is equal to a percentage change in price of 10. What is, a little x over here? What do we got? Negative 12. Okay? So x equals negative 12. So there's going to be a 12% fall, i.e. percentage change in, let me just put it as, sometimes it gets a little funny doing that. The change in quantity equals negative 12%. You can see how much easier that little ratio business is to use, right? That wasn't too hard of math, just kind of manipulate around without getting into this monster and coming down. That's why I wanted to point that out to you. So you do need to know both. So you need to remember this formula Quantity on top, price on the bottom. By the way, on the final, so you can, if you wanted to start making a formula through the, might be a good tip. That way, when I pull out the pop quiz, you can just pull out your formula sheet. Have it all in one spot.
Pop quiz.
All right. Now I'm ready to. Any questions on that? Was that clear? Okay, so back to this. Why is this thing kind of handy? This is kind of useful. Useful for real business because it tells them what to do. Or at least what the efficient thing to do is. It tells them what to do using price, marginal cost, and the elasticity. Now they do have to know the elasticity, or at least have an idea on what that number is. But if all three of these are known, so if they should have a pretty good idea what they're selling the product at right now, right? Hopefully they can reasonably estimate what the cost of an additional unit is. And they might need a little help with that, but if they know the elasticity of demand, now we can use this for decision making. So if the price minus the marginal cost over the price is greater than 1 over the absolute value of the elasticity, if that is true, then what advice do you give them? What advice do you give them? So, well, I want a direction of change. So basically, we're not doing it optimally anymore, and so should they increase quantity or decrease quantity? So if we've got then marginal revenue is greater than marginal cost. So back to this graph, should we be increasing or decreasing where we're at? Where are we at? Marginal revenue is greater than marginal cost. Are we to this side of this anchoring point? Are we over here or are we over here? We're over here, so what should we do? We should increase, yes, or increase quantity, right? So we should increase production. So if that's the case, then marginal revenue is equal marginal cost, and you should increase quantity. If vice versa, of course, you'd back off. What's that? Yeah. This is MBA economics. This is not your undergrad style. All right. I want to do one more with the stay even before we get into income. elasticities.
What's this video going to be able to
I will get it posted now that I'm not going to Vegas at 4 a.m. tomorrow morning. I'll try to get it up tomorrow sometime. So if you don't see it, feel free to email me. All right, so stay even. And I think I was talking to Steve earlier. Hit the book too. You know that it's a short read, right? Short but complex read. But after tonight's stuff, he'll hit it in kind of a different way, but it's the same material. I filled you in with more background information than what he does, so this will be even a little bit harder, but it's still a good, I think he's a decent writer at it, so and gives you kind of scenarios on how it works through. So we'll read through that, then maybe hit the replay on their videos, but I would encourage you to go hit the book next on getting this stuff. So this is called stay even analysis. So, useful for analyzing how much quantity change would be required to stay even from a price change. So, I mean, the typical thing would be, okay, I think we should cut price to raise revenues, but how much more do we need to actually sell to stay even, right? Because I know I'm cutting price, and that's going to be a negative effect on my bottom line. You know, what do I need to do to stay even? So this one is kind of neat that way, because it's going to add in another kind of element to it. All right, so let me just crank out the, give you the formula. I think I'm going to give it to you in all its glory. They do a kind of a two-step way here, but so the percentage change in quantity needed to stay even is equal to the percentage change in price divided by the percentage change in price plus that markup little section, P minus marginal cost divided by price. So that's kind of it in all its glory. It's not as tough as it looks. It's just kind of mathematically comes out this way to, you need to increase quantities by at least this much if you do that kind of price change, right? So you'd be kind of solving this problem. How much? Well, I did that already. Increase price. So let's call it a 10% increase in price needs to be offset by question mark decrease in quantity. I'm flipping it around from going up. So I'm going to raise my price. How much sales am I going to lose? So this is the stay even quantity. Kind of nice because the businesses often have a point in time that they're operating at, that they may not know where other things are, but they know today's sales, they know last month's sales, they kind of know the price that they've been selling it at $40 a unit. what if we went up to $44, a 10% increase, right? So we raised price 44. Well, you would need to not lose more than this quantity to have that make sense. So that's the stay even quantity. And again, data that they probably know, what's the current price they're selling it at, what's the approximate cost per unit, what's that markup. So all of these are kind of known variables, and that's what made this expression kind of a powerful one for people to use in real business. It's like, oh, well, I know that, I know that, I know that, I know that. Is elasticity in here? No, you don't see any E in there, right? Another powerful reason why this is kind of nice for real world business. At least gives you an idea. If you know this, you know this, you know this, you're proposing this, this is the amount that you need to get back to justify it. Now we're back to a gut feeling, right? The elasticity would allow us to actually calculate that, oh, well, you're going to lose 60% in sales, right? But you're still going to stay even as long as you only lose this amount. That's the stay even quantity in terms of revenue. So it kind of gives you that break point, like, should I do it, should I not? Well, that sounds reasonable to me. Or, no way, man, we're going to lose a lot more than that, or whatever. Okay? All right. So that wraps up what I was going to talk to you about in Chapter 6. We're going to not spend, that was a lot longer chapter than Chapter 7. I guess the two things I wanted to leave you with, maybe I will write on the board a couple. We can calculate elasticities for anything. We did that earlier in a sense, or at least our gut was, when we said, well, what if our income goes up from 20,000 to 30,000? How much more will we sell if we have a normal good? Well, that's essentially an elasticity. So this whole time we've been looking at the price elasticity of demand, but a couple other ones that I want to call to your attention. So two other elasticities. Number one, the income elasticity. Maybe we'll call it EI. Conceptually, that elasticity is just looking at how much quantity changes from some percentage change in income now. Instead of having price downstairs, we have income downstairs. No big deal after what we've already been through, the big hurricane we just survived. The questions and kind of the solving of it would be similar. If income goes up by 10%, how much more are you going to sell? Well, if you know the income elasticity, you can answer that question. Okay? Questions on that? All the rest of the math and stuff would all be the same for the calculation too. Number two, the cross price elasticity, Coke and Pepsi, peanut butter and jelly. We just look at the change in the price of a related good now. How does the quantity change when there's a percentage change in the price of a related good? So like we saw earlier when we started off tonight, Coke and Pepsi is going to have a cross price elasticity. Is that number going to be positive or negative? So I like to just do it this way. Price of Coke goes up, quantity of Pepsi demanded goes Up, right? Pepsi. So price of Pepsi goes up, demand for Coke goes up. Price of Pepsi goes down, demand for Coke goes down. The sign of that elasticity then would be positive or negative? Positive. They're moving together, right? So the elasticity would then be greater than 0, a positive number. If we're talking PB&J, peanut butter and jelly, the cross price elasticity is going to be the opposite. Peanut butter goes up, prices of peanut butter goes up, we sell less jelly. The demand for jelly goes down. So it's going to be less than 0, a negative number. Now, since Ryan brought this up earlier, what if it's 0? How are the two goods related to each other? It stays the same. They're not related, right? So they're unrelated. So as we estimate that, so if the cross price elasticity is equal to 0, then we've got unrelated goods. So we've got unrelated goods. Some goods we're not sure maybe what their elasticity is. Our gut feeling, it's maybe not as easy. Like you might think beer and wine, substitutes or complements? Substitutes. Justin, beer and wine.
Depends on the night.
Okay, depends on the night. Mixing it up a little, right? If you're throwing a party to a big group, do you want to have only beer or only wine? Or would you have both? You might have both, right? You don't know who's coming to the party. You're expecting about 50 people. Do you just want to assume that they're all going to suck off the keg, or do you get maybe some bottles? You get a keg. You get some white wine. You get some red wine.
So where are we going?
So those two are. Now I'm getting you guys excited again. All right, good. Those two might be substitutes or complements. We don't necessarily know going into it. So then we use statistical analysis and crank in a bunch of real-world data and let the data tell us. So now, when that number comes back and it's a negative number that we calculated for the elasticity using some complicated statistics, not even that complicated, but we learned that they tend to be substitutes, or we learned that they tend to be complements. But we maybe didn't know that going into the study, is all I wanted to point it out there. And that's why we use elasticities. And then the value of the number, maybe more importantly, tells us the strength of the correlation between the two. If the number is a 4 versus a 1.2, the 4 has a stronger correlation to it, right? In fact, when we get into complements, we might talk about peanut butter and jelly, but if we talk about instead left shoe and right shoe, right? So what is the price that I'm willing to sell the complements for the left shoe and the right shoe? They need to be together, right? For there to be any value to me as the consumer. And so there's a high number, a high complementarity between left shoe and right shoe. So that number would be really big when we're talking about left shoe, right shoe. Peanut butter and jelly might be down the spectrum a little bit more. So the value of the number will determine how strongly correlated those two are. When you look at that, that changes your results here when you start doing some of this fun stuff, right? If this is a 4 versus a 2, you get a different answer. So these results depend on the elasticity of demand. It really depends on all of these elasticities to some degree. Okay. Fun stuff.
We call it a night.
Are you starting to get fried? We're getting close. We're getting close. we're gonna do this next chapter is very, very short actually. So that's part of the way I'll try to turn it in early here. How about that? So,
Just one YouTube video we have to watch the video.
three main topics that are really kind of related to each other and important. In fact, I think we've talked about it earlier. And so we're going to start off with economies of scale. Remember when we talked about Walmart and they were way at the other end of the curve? So we've kind of this is already a review. So economies of scale. If we look at our cost curve that we all have memorized now, and we think about production of a good. So let's say that we are a manufacturing firm that does chrome pieces, chrome tailpipes for an auto manufacturer, right? So here we are, quantity of chrome pipe. And we started off our business and we tended to be doing about 200 pipes a week. And we found that the cost associated with each chrome pipe was running about $250. So that gave us a point here. And let's say that when we started off, that was pretty efficient. We had about a 10,000 square foot garage, pole barn type of thing. So this was our average total cost associated with a 10,000 square foot garage manufacturing plant for our metal pipes. So we kind of grew into it, right, as we started to get volume up, and we've kind of reached this point. Now what we found is we got an order in, and 1 week we were at 300 units. Now, when we're pumping out 300 units, given our factory, we're kind of giving it a little bit overkill, right? It's starting to get a little crowded in the manufacturing plant. But we got 300 people, we got 300 pipes to kick out, we got to do what we got to do, and we do it. And so what that means is do it a little bit differently by getting building. Decision. It's a long-term decision, right? So that was buildings, especially in capital equipment and whatnot, were one of those things that we kind of want to be careful on. And so week after week, after month, maybe even after year, they tended to start to do more volume of business. And you're like, Fred, you know, we've been in this building since we started the business. I think it's time to get into something bigger. I think we can be more efficient if we just had 20,000 square feet for the additional machines. And so let's just say that they were able to drop their costs down to $200 by being in a bigger building, by reallocating where they were at. If they're staying at that point, they could be in a 20,000 square foot plant, kicking them out at $200 in cost, and of course making more money. But in order to justify that, all those additional variable costs and the additional fixed costs, they have to be regularly going at that higher volume. Because if they fall down, they're back to where they were before. Now look at even worse yet. If they go down to 100, if the economy tanks, now look at what happened. They would have been better off in their smaller building than in their big building. Right? So that's the trade-offs that they're thinking about. You got to have the optimal mix of labor and capital and be thinking about that mix depending upon the volume that you have. All right, and then let's just do one more out to 400. We could continue to do more, but I think this will, since Ryan is anxious to get out of here, we won't drag this out any further. Let's say they weren't able to drop it down quite as much as they did before, but they were able to drop it down to 180. And so if they got into a 30,000 square foot building, they could be at that cost. All right, so what we've uncovered is what economists refer to as economies of scale. By increasing the scale of production, we're able to bring long-run costs down. These are short-run cost curves. Again, if orders fall off and we're sitting here in the 30,000 building and we drop down to 200, cost per unit's really high because you still got to pay the rent, you still got to pay the market, right? You still got all those fixed costs. We're looking at total cost here. You still got to absorb all that even though your costs are low. So you're not able to spread that out. And so we end up getting this concept. And now our long-run decision starts to jump out at us. We could be at some optimal square footage no matter where we were, right? And so the long-run curve is essentially the outer envelope of the short-run curves. So the long-run curve, you can kind of connect those points and just kind of make your own point. This is long-run average costs. When you draw this, I want you to flatten it out, though. Come to kind of a flat spot, and then you can even turn it up a little. And this would be long-run average total cost. And the range at which long-run average total cost is falling is called economies of scale. So in short, an increase in quantity leads to a decrease in, or is associated with a decrease in long-run average total cost. Okay, so questions on that? So there's an infinite number here, right? Finding that in the long run we have the chance to re-optimize everything. All costs are variable in the long run, so that's what that cost curve looks like. Because really, remember, this is the long run average variable cost because all costs are variable in the long run. Now, this little point here is possible, called diseconomies of scale. And it's a little bit tougher to conceptualize, but maybe not if you've been associated with a large corporation. So you got maybe management, lack of communication, information's harder to get around to everybody in the organization. You can think of these little guys starting out of their garage as being very nimble and quick and being able to make decisions, and I yell at Joe across the cubicle and he hears me and I say, let's go do this, and we go. But in a big organization, you might run into diseconomies of scale, where eventually you get so big, it's difficult to manage, and that effectively drives up cost. All right. Economies of scope. Economies of scope. Yes, economies of mouthwash. So So economies of scope deals with multi-product companies, first of all. So it's kind of similar to what's going on here, but instead of thinking in terms of volume of one good, we're going to think about multiple products and spreading overhead costs over multiple products. So a multi-product company, the idea here is that the cost associated with production of Q1, Q2 jointly is less than the cost of them separately. We'll throw on our equation goggles first, even though I know you guys are ready to throw those things in the garbage right now. But okay. This one kind of reads nicely. It's kind of cute. So we got the joint production. So you can kind of think of this as the joint production of both is less than if you were to open up a company and do everything separately. All right, so this is the sum of separate production. So if the cost of joint production is less than the sum of separate, you've got economies of scope. I guess if we turn this into a if-then, we got a big if here. If that, then you have scope. Could be distribution. There could be a number of things. But yeah, think about the supply chain. Yeah.
Things stay the same regardless of the tab.
So I was just out at Cargo Tech last week sometime, and first time I've been up there, and they have a shipping area. It's a big company. You guys familiar with it? Big employer in Ottawa. One of the bigger employers. They hire a bunch of engineers. Good community player. Blah blah blah. All that. And so they were helping us out. I did some stuff for this nonprofit in town with my son's Suzuki program. He plays violin. And they were helping us ship some stuff because they get a lower cost of shipping. And so I was kind of surprised to see they had basically a whole building set up of where they're shipping stuff out because they do multi-product stuff. Right, so you imagine if they had a single product that they were doing, they might still have to do a certain volume of shipping, or they might have to hire it out to FedEx or something. And so maybe they started getting 1 or 2 products and they had a certain shipping size unit. But now for all 5 products or all 10 products, or I don't know how many products they do up there, they've got this one centralized place where all the shipping goes through. Right? So that function, the average cost to ship, to open up a new product line, the variable cost associated with shipping that new product out is less than what it would be if you were just starting from scratch, right? So you see this all the time with companies. Most companies, I shouldn't say most, a lot of companies have some sort. Maybe it's just 2, or maybe it's, if we look at a place like Walmart and count the number of things on the shelves, they've got a multi-product thing going big time. All right, so that is economies of scope. Questions or comments there? The last thing is just to mention something you already know, but just kind of think about it now that we got you geared into cost, and that is the learning curve. What do people usually mean when we think that there's a learning curve?
Usually how it's used is how long it'll
Right, right. So if we think about how much effort it's going to take and how much production, if we have productivity here, this is kind of a weird graph I'm doing off the top of my head, but you just made me think about it. That learning curve probably looks like this, where you've got to put in, well, let's see, does it look like that? What does this function look like? I might be a little bit wrong here. Well, you tell me, Steve, what were you thinking? So effort level or amount of time, effort?
We don't have a Steve at class.
What am I doing here?
I'm sorry, what was I thinking? I was thinking that how most people, I think they use it incorrectly, but learning curve is a function of time, isn't it?
I thought it was.
Yeah. Oh,
time
you fixed that.
So how much time does it take you to do the first?
Well, it has
Yeah,
a
it's-
high learning curve.
Is what time is what?
And what? Yeah. So what does that look like in terms of? So we could think of it being kind of cumulative, possibly, right? So if you can do something in less time when you know it better, right?
So when your learning curve is high, it takes less time. Less time and effort.
Okay. So production gets higher when effort gets lower.
No, time. Why are you saying effort?
Okay, let's go time. So time it takes. This is where it gets into that marginal stuff, total stuff.
So time is low and production is high.
Time is low, production is high. And then time is high,
Production.
low. I saw Skylar doing some sort of circle thing. I don't know, you're kind of going like this. I wasn't sure what that.
Saying like, the longer you learn something, you spend time on learning something, basically the more knowledge you get,
So this would be cumulative time, right?
like the more knowledge you get on something, not even production.
So if you put in 8-hour work days,
Production is like a maximum 20 days.
how about this one? If you put on 8-hour work days, let's see, what's 32? What does this look like? How much do you do your first 8 hours of work? High or low? So that's going to be low. Okay. And then 8 hours, what does that look like? So if we did 10 units here, my next 8-hour shift, what does it go up to?
20.
20, which would be the same. So in terms of the learning curve, are you better or worse your second 8 hours versus your first 8 hours? Are you more productive or less productive?
If we're assuming
More.
that
It could be both. It depends on
If
the
it,
person individual.
if we're thinking back to Jesse's first learning curve thing here,
are we assuming that we're putting out the same amount of effort, not getting tired?
Maybe it's
yeah,
more
we're
the
learning. So we're on learning curve. So there's some learning that needs to be done. So you're kind of stupid at the first 8 hours. Then you get a little smarter and a little smarter and a little smarter, and at some point you reach maximum efficiency. So if you stay there for the next 5 years, you're not likely to gain any more in terms of the learning curve. So at 16, am I less than 20 or greater than 20?
Say 22.
22, which would imply what?
That you're greater.
That you were more productive, right? So you learned something from the first 8 hours, right? So 22 or something like that. So now we're going up, next 8 hours. Now we're jumping up to whatever, 35. All right, so this thing kind of goes like that. Now, when we start to be able to do the same like we were thinking, now I can do, let's see, what do we got here? 10, 13 units? if we kind of plateau now and we've learned everything that you're going to learn, what does that look like the rest of the time then? Work 8 hours, get 13. Work 8 hours, get 13. Work 8 hours, get 13, right? So now we got this. So the learning curve here in that context was an acceleration over the early hours. Now,
Well, now, hold on.
I don't like.
Now with this, when you say production, are we talking about actually producing something? Like,
yes,
okay, so that like 35 is 35 widgets, not 35.
could be dollars worth of product sold, I suppose. I mean,
Because I'm making sure that the production's not all being, you know what I mean?
well, where we're gaining it here is at the margin. So the first
Okay, so
8
that's-
hours was that amount,
Gotcha, okay.
but now we got that amount, and now we plateaued at that amount. So boom, 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 the learning curve got us more productivity as we went up.
Okay, I see.
How does that translate into cost? Where were you more cost efficient for this particular company at when you first started or later? Later, right? So that's the whole connection to cost. So your cost curve goes down as you get more time, right? Because we're measuring it in terms of production. We better call it a night there.